All right, ladies and gentlemen, welcome back to another video with Mr. Kenton in AP Chemistry. We're getting close to the end of Unit 5. We got two more sections, and today we're going to be looking at multi-step reaction energy profiles. So if you think back in Unit 5, Section 5.6, we plotted reaction profiles for when there was only one step, right? But as we've seen, we can see mechanisms that have multiple steps. So if we know the energy components to each of those individual steps, then we should be able to present or produce a reaction energy profile for all those steps. The other thing, we could make approximations based on how things would look as it pertains to maybe their activation energy and things like that. So hang on tight. This should be, I think it's going to be pretty good. So let's dive right in here to multi-step reaction profiles. So we already know that if we know the energies of our reactants and products and our transition state, we can construct a reaction profile for a reaction. Well, if you know that same information for multiple steps, then you can construct a multi-step reaction energy profile, right? And just some things for us to consider, just if you're given something like this, some simple things that we should be able to do is to determine how many transition states do we have, right? And so, and that'll also help us determine the number of steps, right? And so if you see that there are two transition states, like what we have here are activated complexes. We've got two activated complexes. That means we have a two-step reaction energy profile. We have a two-step mechanism. Okay. The second thing we should be able to determine from a multi-step reaction energy profile is what's the rate determining step or the slow step. And the thing that we're going to look for there is whichever step or whichever activated complex has the largest, well, let me just say activated complex, whichever step has the largest activation energy, so the greatest difference between its reactants and its activated complex, so here and here versus the energy here versus the energy here, whichever one of those has the highest activation energy, that's going to be your slow step. So if we're looking at this particular example here, that means that step 1 is our rate determining step because it has a significantly higher activation energy. And the other thing that we should be able to identify from a multi-step reaction profile is the intermediates. Where are the intermediates in this case? And so we can see here that the intermediate is going to be at the valley, right? So there's going to be one intermediate that's going to show up in this mechanism. Now, for this particular graph overall, we can still see that even though it's multi-step, if you check the difference in energy between reactants and products or products minus reactants, we end up with something that's exothermic. The products are lower in energy than the reactants, so it's going to release energy. We can look at it from just analyzing the graph. We can see that the first step is endothermic. So step 1 is going to have a positive delta H value. So the difference between here and here is positive. And like we stated, the last thing here, the rate determining step is the first step because the activation energy for that step is higher. All right. So hopefully that makes sense. And really what I'm hoping to do in the next couple slides is maybe to walk through a couple of examples with you. And hopefully that'll help kind of contextualize and give you an idea of where you need to go from there. Right? And so what we've done here is we've taken the reaction energy profiles for several of the reactions that we've already looked at and constructed the energy profiles, right? And so we can see here for this particular process, we're seeing, okay, step 1 is the slow step. That's where our first transition state is. Here, so step 1 would certainly be endothermic because the difference from here to here shows that it's endothermic. We've got our second transition state with our much smaller activation energy, so that means it's a fast step. And then we go to our products. We see that step 2 is exothermic because the products are lower in energy than here. And then overall, we see that the product energy is lower than the reactants. And so this first one would be exothermic. So it's a two-step process with a slow first step, fast second step. And then in our second profile that we've been given here, separate reaction, we've still got two steps. But here we see that the first step is the fast step, and the second step is the slow step. We still have two transition states, one here and one here. Got an intermediate here. First step is endothermic, and our second step is exothermic, and our overall process is exothermic as well, right? So just to look at those and be able to break those down. Now, let's say you're asked to do something where you have to construct your own. So let's say that you're asked to draw the energy profile for the reaction of T-butyl bromide that is transforming into T-butanol in the presence of hydroxide. And they give you the steps. They tell you the first step is a slow step, second step is a fast step, and they want you to construct a reaction energy profile. Now, for this particular setup, one thing that I'll say is a limitation to this one is they don't tell us the energies respectively of our starting energy of our reactants and products in both of these cases. So we're going to have to kind of arbitrarily assign values. So what I'm going to do is I'm going to draw a graph, right? This is going to be energy on the y-axis, and this is going to be reaction progress on the x-axis. And so we're going to have 0. I'm going to do this in increments of 100, 100, 200, 300, 400. I think that's probably sufficient, right? And so the first thing that we note is that the first step is a slow step. So we should draw this so that it has a higher activation energy, is going to be a slow step, but the overall energy change is 90 from start to finish, right? So I'm going to have kind of a starting point. I'm just going to pick 200 arbitrarily here. So my starting point's at 200, and I know it's going to need to go up to about 290 for my final, right? So if you're following along with me here, that means that my slow step ends somewhere in there, right? So we've got something like this. That would model our slow step. So that's step 1. And then for step 2, we see that the change in energy from this point, which would be at 290, and the products would be, there's a decrease in 100 kilojoules. So we're going to go down to about 190. So I'm going to come over here, and I should have my products that are somewhere over here. Now, this is a fast step. So my reaction is going to carry out. It's going to go up. And we get something like that. Right? And so just to kind of label everything, we've got, this is reactants. This is products. This is our activated complex 1. So activated complex 2. And then this is our intermediate. Right? Now, if we want to start showing energies of things, right, we could show that the activation energy that's EA1. That's going to be EA2. And then for our overall process, right, this would be delta H of the reaction, and it's going to be less than 0, right? And so from this, we can see that the activation energy for the first step is larger. Second step is smaller, so that shows the slow and fast step. We see that the overall process is exothermic. In fact, we should see that it looks like the overall energy difference would be about -10, right? And so that's how we would construct the reaction profile given the information that was provided here. Okay. Now, we could be given an example where they give us much more data, like on the next slide. So the next slide, they were nice enough. They gave us the energies of everything, and so now they want us to sketch it out, right? It actually asks you to do it, so I definitely think you should pause the video and do that. Do it on your own, kind of construct your graph, and go from there. And then when you're ready, come back and watch me go through and do it. So hopefully you've done that. And I'm just going to start by plotting the information that we have here, right? So we've got the reactants are at 20 kilojoules per mole. So I know that I've got something right there. My first transition state is at 80 kilojoules per mole. So that means it's somewhere in here. My intermediate is at 50. So we got the intermediate's going to be somewhere in here. My transition number 2 has an energy of 90. So I'm going to come over here. That's going to be somewhere in here. And then my products are at an energy of 5. Right? And so then if I want to construct my diagram, I'm going to have something that looks like this. Oh, oops. Mr. Kenton started off on the wrong foot. Hopefully this doesn't erase everything. Well, it didn't erase everything. It just erased my line. So I need to go up. My activated complex is here. My intermediate's here. Activated complex is here. And products are there. Right? So that's what your reaction energy profile should look like for this particular process. Now, you start looking at things, we can actually provide specific values. We could say that the activation energy for step 1, which would be here, should have a value of the difference between the transition state 1 and the reactant. So this is going to be 60 kilojoules per mole. For the second step, activation energy is going to go from here to here. That's going to be approximately 40 kilojoules per mole. And then if we wanted to look at this for delta H, energy is being released, and it looks like delta H has a value of 15, or it would be negative 15 kilojoules per mole. Right? And so from that, again, this is our transition state 1 or activated complex 1, transition state 2. This is our intermediate. We know that the first step, because it has the higher activation energy, this is going to be the slow step. So step 1 is slow. Step 2 is fast. And this reaction is exothermic, right? And that's how you would construct a multi-step reaction energy profile. I hope this video was helpful. Hopefully it was insightful. If you do have any questions, feel free to fill out that Google form or bring your questions to class, and I'll be more than happy to address your questions, guys. Thank you so much. I'll see you guys soon.